Good afternoon, everyone. Welcome to this scientific section, Hydrometeorology, Atmosphere, and Extremes. So I'm the chair of this section, Yan-Ping Li from University of Saskatchewan. In this section, we will have 5 presenters. Each of you will be given 10 minutes and QA after each presentation. The first presentation will be given by Manoj Namvel from University of Quebec at Montreal. Manoj, it's your turn now.
Thank you. Good afternoon, everybody. Thank you for coming for this presentation. So I am presenting about, we are comparing 4 different satellite derived precipitation products over the Western Canada. So precipitation is the key input variable to hydrological models and plays an important role in water resources planning. However, its accurate estimation is challenging, mainly in areas with sparse observations and region with complex orography. Like there are diverse satellite-based precipitation products. We usually depend upon them because the rain gauge data, the direct observation using rain gauge data is often not practical and not economical. Remote sense data is often used. So before we use this data, it should be cross-validated against the observations. So Western Canada is one important region where there are lots of flooding events happened, like the famous 2013 Calgary events. So we would be testing different satellite-based precipitation products. It include the MSWP, CMORPH, GSMAP, and iMerge against the surface meteorological station from Environment and Climate Change Canada. So these are the satellite products we are using. They are high resolution satellite product with all of them are around 0.1 degree spatial resolution, and MSWP is 3 hourly resolution, temporal resolution. CMORPH is 30 minutes, GSMAP is hourly data, and iMerge is 30 minutes. And the true data we are using as the Environment and Climate Change Canada, the weather station and network data. Those are hourly data. We will be testing the satellite product both at daily and 3 hourly time scale. So 3 hourly time scale is the temporal resolution of the MSWeb data. So the minimum precipitation amount used is 1 millimeter cutoff for the daily data and 0.2 millimeter for the 3 hourly time scale, respectively. And the time period of this study is from March 2014 to December 2020. So we have used a total of 125 stations. They are divided into 6 climatological regions. So we have more stations in the southern near the southern Canada and less stations and towards the north. So we use the metrics such as the Pearson correlation coefficient, root mean square error, and standard deviation to validate its performance. So these are the study area, and you can see a different colored map which indicate different climatic zones. So we have the Pacific Northwest, the Great Basin, the North Rockies, the Prairies, West Taiga, West Taiga and West Boreal. So this is the annual cycle of the mean of monthly accumulated precipitation against each month. We have here 7 years, approximately 7 years of data. And these are for different regions. This is for West Boreal, Pacific Northwest, Great Basin, North Rockies, North Plain, and West Taiga. So here, what we can see is in all the diagrams, all the satellite product show it is comparable to the black one is the station data. So its performance is comparable to the station data, except for CMORPH in the winter. In summer months, all are having similar performance. But in the winter, the CMORPH performance is not good, except for the Pacific Northwest. So that is because CMORPH has some difficulty in observing the solid precipitation and weak precipitations. Another thing we observed was the MSWEP. It's in magenta, and the blue it's IMERGE. They overestimate the precipitation in all the stations. That is more evident in the case of the Pacific Northwest. So all the satellite-based products except CMORPH are in reasonable agreement. CMORPH performance is not good for colder months. So this is the precipitation data accumulated at a daily time scale. We use a Taylor diagram. In the Taylor diagram, on the this one on the x-axis and y-axis, these are the standard deviation, and we have this on this axis is the correlation, and here we have the RMSE. So if it is two in the right, you can see a star. That one is the reference data. So if it is on the right side, it has high correlation, and if it is close to the station data, then it has the best performance. So across all the climatic region, so you can see the magenta one, so that is the MSWEP, it has the highest performance. So here the small dots are the individual station data, and the big dot are the mean of all the stations data in a particular climatic regions. So if we look at each data, so we have a minimum number of stations in the West Taiga region. So like in the West Boreal and in the Northern Plain, they have the best performance for the MSWEP, and the worst performance is in the North Rocky region, where mean is here. And also the CMORPH has the least performance in all the regions. So the overall the better performance of MSWEP can be attributed to it is calibrated at a daily time scale, whereas the other data are calibrated at monthly time scale. So this is for the daily time scale, and here in this diagram, this is the mean for all the stations in each regions. Here we can see that the correlations and the skill altogether decreased from the daily data. So that is again because the calibration is performed at the daily time scale. Also, another reason could be the MSWEP also contain the ground station data. So maybe some of these station data are also used in the MSWEP preparation. Here we have the at daily time scale, seasonal. We checked at different season how their performance. So what we could see that like in all the stations, the star is the winter and the square is the summer. The winter has the worst performance and best performance in the best performance in the summer. So it can be attributed to the rain gauge are better capturing the precipitation in the summer months, and wind and other things would have disturbed their capturing in the winter months. So this is the summary. So all the products show higher skill at the daily time scale. So MSWEP precipitation estimate is better than the other data sets, both at 3-hourly and daily time scale. So MSWEP perform better because the calibration is performed at daily time scale, whereas the other data are performed at monthly time scales. So all the satellite-based product estimate perform better in prairies and lowest performance is noticed in Rockies because the satellite product has some problems in higher the complex topography in observing. So all the products are in reasonable agreement with the station data for Pacific coastal region. And also another thing is all the products have the potential to complement the GOAL data, but the CMOR performance needs to be improved considerably in the winter months. So these are some future directions. So we are also doing a higher resolution 3-kilometer GEM modeling, and we will use some of this data to cross-validate the GEM model simulations. Also, we would study some like extreme events using the satellite data as well as the model data. Thank you.
Okay, thank you, Manoj. Any questions for Manoj? Oh, okay, I do have a question. I just wonder, like, you look at the annual cycle and like the performance for different data set varies, but in general good. I just wondering, have you looked at the extremes, like the extreme for different?
No, we haven't looked that. So maybe that is our next study, like a study the extreme events. Yeah, next part.
Okay, so for different data set as well, not just for like
yeah, yes, for
model
different for different data sets as well as our modeling result also we would check for the extreme events, like the last flood in the BC. Yeah.
Okay.
Fall flood. Yeah.
Okay, thank you.
Yeah, thank you.
Thank you. Let's go to our next presenter, Francis Wells from PICIC. Welcome, Francis.
Hi, Yang Pin, and hi, everybody. Thank you. I'm just in the process of sharing my screen. So you should be seeing that now. So I'm going to very quickly report on a rapid attribution study of the flooding event that occurred in the middle of November in British Columbia. So you see that there's a very large team that's listed there of people who worked on this from the Climate Research Division of Environment Canada and Meteorological Service of Environment Canada and PICIC. The paper is now published in final form. So this study was done pretty quickly, submitted, reviewed, revised, and published. You can get it from Weather and Climate Extremes. It just appeared a few days ago. I don't need to say very much about the damage that occurred. So everybody has seen these images, various images of the damage that was suffered in British Columbia. Essentially, all of the surface transportation network was put out of service between Vancouver and the rest of Canada. So disconnecting biggest port in Canada from the rest of the country. So that included highways, rail lines, and pipelines. The event that occurred was occasioned by an atmospheric river event. So here are some figures that show you the synoptic setup that prevailed during the time of the event. So you can see the left-hand column of figures show surface pressure, the 500 millibar geopotential height, surfaces and anomalies. And so they show that a very tight pressure gradient was set up that directed moisture from the subtropical Pacific directly into the Fraser Valley, the little box on the in the panels on the right-hand side on those 3 days. And so there's a very classic type of atmospheric river event. The atmospheric river itself was not that rare an event. It was estimated to be something like a 1 in 3 year event. If we look specifically at westerly atmospheric rivers that drive moisture further inland, then this would be a 1 in 10 or 1 in 12 year event. And perhaps if you consider even more carefully the topography, you'd conclude that it was a substantially rarer event than that. If you look at the convergence, moisture convergence that was produced as a consequence, that turned out to be a much rarer event of the order of 1 in 50 years or so. Here's what the resulting precipitation field looked like, the cumulative precipitation over the 2 key days, November 14th and 15th, as derived from Kappa in colors and stations. The little circles that are shown, the black box is the main study area that we considered. The lower panel shows you the annual maximum 2-day precipitation amount averaged over that study area from era 5 in blue and from Kappa in the rusty color. And what you see is that the November 14-15 amount really stands out, particularly in Kappa. So as a precipitation event averaged over that area, it looks to be of the order of a 1 in 50 year event based on era 5, roughly a 1 in 100 year event based on Kappa. And the assessments from station data, which are variable and uncertain, are of a similar order. Here's a description of what happened in one of the drainage basins that was affected, and these figures describe the event that occurred as it occurred in the Coldwater River. The Coldwater River flows alongside the Coquihalla, the main expressway out of Vancouver, and in a northeasterly direction up to Merritt. And so in the upper right-hand panel, you see precipitation as it occurred. So you see the event beginning about November 14th, intense precipitation on the 15th, trailing off on the 16th. The black curve shows cumulative precipitation over that period of time. The green curve, turquoisey type of curve shows the sum of cumulative precipitation and cumulative snowmelt. And so the total input into the basin in the form of liquid water over that period of time was something like 150 millimeters. You see what happened in the second panel to the snowpack. It initially grows, and then a lot of melt occurs, and ultimately by the 17th is more or less depleted over that period of time. And so that contributed about 20% of the input to the basin. The third panel shows the air temperature profile over that period of time. So you see that melting begins, temperatures rise well above zero, beginning on the 14th and then extending through to the end of the event on the 16th. So that's when most of the melting occurs. And the discharge that was recorded in the basin is shown in the lower panel, with discharge rapidly rising between the 14th, 15th, and then beginning to tail off again on the 16th. So of course, those numbers are very uncertain. Similar analyses were done on other basins. And what we learned by doing those analyses is that in each of those cases, we see that the event was large, that snowmelt was important, but not the dominant factor. So what you're seeing here is the 48-hour normalized discharge on the vertical axis for each of those basins, and on the horizontal axis, 48-hour precipitation. So we're showing the ratio between discharge and precipitation. Sometimes those ratios are bigger than 1, and that has to do with very substantial melting of the snowpack. For the event that occurred, the blue circle with the red dot inside, we see that discharge as a fraction of input, precipitation input, varied between 0.43 and 0.76, depending upon the basin. So snowmelt was important, but not dominant. This was a rapid attribution study, and so an important part of this study was for each of these components to try to judge what the effect of human-induced climate change might have been. We were very fortunate to have access to a large ensemble of hydrologic simulations for the Fraser Basin. And so we're able to ask this question for several of the tributaries of the Fraser, including the Coquihalla River. And so what you see in the upper right panel is a flood frequency distribution for large discharge, simulated large discharge events in the fall season, October, November, December. 100-year event in the historical climate, as shown in black, in the warm climate of the present warmer climate, shown in blue, and you can see that human influence on the climate system has, at least as simulated in the model combination that was used, has an influence on discharge. The estimate is that human-induced climate change may have increased the probability of extreme streamflow events of the type that we're seeing by a factor of 2 to 4. When we look at precipitation and the atmospheric river event itself, we come to very similar kinds of assessments. And so the conclusions are as follows. The atmospheric river itself wasn't a particularly unusual event. The two-day precipitation event was substantially more unusual. Stream flow exceeded a 1 in 100-year event magnitude in several locations. Precipitation was the dominant factor in deriving extreme flow. Human-induced climate change appears to have substantially increased the probability of an atmospheric river event and the resulting precipitation and flooding. The June 2021 heat dome event and 21 wildfires may have been a factor affecting drainage basin function and also preconditioned in the drainage basins. It was a very wet fall. Cumulative precipitation over the fall was tracking near record levels throughout the fall in all of these basins at the time of the event. And so maybe the basin condition had been changed, but also land surface was essentially saturated at that time. And so that's it for my presentation. I'm happy to take questions if there's any time left.
Okay, thanks, Francis. Any questions for Francis? Francis, I just wonder, like for the different factors, like the precipitation and stream flows, they are from different data source, right?
Yes, so we used kappa, we used reanalysis data, we used station data. We did ask about the consistency of the information in those different data sets and the consistency of information across different facets of the event, the atmospheric river versus the resulting flooding that occurred. And I mean, there are very large uncertainties in some of this data. The stream flow data, for example, is very preliminary. Gauges are damaged in the process of an extreme event like this, and so it's only well after the fact when the gauge data has been carefully recalibrated that we begin to understand a little bit about what the stream flow was. But even then, uncertainties could be very large.
Oh yeah, that's what I was wondering, like the consistency of different data set, like when you're converting them to millimeter per hour, like yeah, thanks for this clarification, and I think this study is really helpful. We should expand it to the to the major cities like Calgary or Saskatoon, or like to see if this extreme events is going to be more extreme in the future or something like that. Yeah. Okay, thank you. Any question else? Or we can move to our next presenter, Dr. Muhammad Ali Ben Alaya. Hello.
We don't hear you, Ben Alaya. Yeah, and Ping, maybe you could move on to the next talk, and then Benelli could sort out his
Okay, sure.
technology issues.
Sure. So how about we go to Mustafa? Mustafa, Kamal, can you do first, and then Muhammad will be next.
Yes, I can do that. Can you see my slide? Yanping, can you see my slide?
Yes.
Okay. Can everyone hear me? Hello.
Yes.
Oh, okay. Okay. Good afternoon, everyone. My name is Mustafa Kamal, and I'm a 48th PhD student in the School of Environment and Sustainability. Today, I'm going to talk about the dynamical and thermodynamical characteristics of the supercell thunderstorms over the Canadian prairies. So, have you get scared when you hear a thunderstorm warning of a hail of this size, ping pong ball size, which is about to hit your fancy car? Or do you have a farms, or do you know any relatives or your friend have a farm in the Canadian prairies, and who have sufficient reason to be concerned about a severe thunderstorms that about to trigger a hurricane force wind or a catastrophic hailstorm? So this is the type of storm I have been studying, and I'm trying to understand the dynamical and thermodynamical characteristics of these types of thunderstorms, which is called supercell thunderstorms. And this kind of thunderstorm is really infamous for producing tornadoes, hurricane force wind, and the ping pong ball size hail. So every year, on average, Canadian prairies receive 130 severe hail events, 43 tornadoes, and 45 to 50 severe wind events. And most of them are triggered by severe thunderstorms. And a study shows that 75% of the observed tornadoes are produced by supercell thunderstorms. So as you can see from this map, a study done by Sales, which David Sales, which shows that in the Canadian prairies, those tornadoes are very much concentrated on the southern part of the prairies, and mostly that high intensity tornado events, which are specifically concentrated on southeastern and southwestern part of Saskatchewan and southwestern part of Manitoba. And the bottom panel, you can see that this is the drought maps 2021. And as we know that 2021 was one of the recorded drought year in 20 years. And it is another reason my motivation for studying this supercell thunderstorm, because Canadian prairies, where every single drop of water is important, and more than 80% of the water during summertime comes from the severe thunderstorms. So supercell thunderstorms are of 3 different types, which are called LP supercell, classic supercell, and HP supercell. And LP stands for low precipitation supercell, HP stands for high precipitation supercell, and the classic supercell. So as you can see from the name, that low precipitation produces extremely low precipitation, almost nothing. On the other end of the spectrum, high precipitation supercell produce vast amount of rain, and which can cause catastrophic flooding in the urban areas. And on the other hand, in the middle panel, classic supercell, which is really infamous for producing tornadoes. So these are all 3 different types supercell are interrelated, because under very strong wind shear, low precipitation supercell dominate. Under medium wind shear, classic supercell, and under very low wind shear, it's HP supercell. So, and these three supercell also differ in their characteristics, as you can see from the schematic diagram, and very simple structure for the low precipitation supercell and very light to moderate rain, and those middle panel classic supercell and the HP supercell. So I try to understand that how these supercell forms or how it evolves over the Canadian prairies, because to the best of my knowledge, there is no comprehensive study that focus on all three different types of supercell, and specifically the simultaneously dynamical and kinematical characteristics. So I analyze sounding derived parameter for these three different kind of supercell. So specifically I at first find particular case studies, low precipitation supercell, and then look at the radar characteristics and followed by a sounding analysis. So you can see from this plot a comparison of the surface, the caves. You can say there were two different types of cave, which is called surface-based cave and the most unstable cave. And we can see here that here LP supercell, HP supercell, and classic. So the first three columns and the bar box and whisker plot is showing comparing that the cave surface-based cave, and the right three box and whisker plot is comparing the most unstable cave. As you can see from this figure, there is a clear difference between these three different types of supercell. So that means LP supercell require very low cap compared to the HP, and where classic supercell require the highest amount of caps. The same is for most unstable cap. In the right panel, you can see that which is called downdrop cap, and downdrop is a variable that gives information about the potential for the like a hurricane force wind, and also it gives some information about the hail. So as you can see from this figure, that LP supercell had the lowest amount of down cap, and HP as medium, and followed by the highest for the classic. So I will connect how it refers that why it is important for the D cap in the later slide. And in the second slide, it is I'm comparing the kinematical variables, that the variable related to the wind. So one of the key ingredient for producing supercell thunderstorms is the vertical wind shear. So a wind speed, changing wind speed with altitude, and at the same time changing direction with altitude. So we can see the speed shear and the directional shear, and those are the two variables. When you connect it, it gives like a strong relative velocity, which is a measure of streamwise vorticity, which provide information specifically that with high value greater than 150, it produces the rotating cloud structure, which is we call the mesocyclone, and then also that it distinguishes a thunderstorm from tornadic to non-tornadic. At the same time, in the right panel, you can see the bulk wind difference, which is the vector difference between the wind at two different levels or altitude. And again, you can see very clear difference between strong relative velocity and as well as the bulk wind difference. And then we compared that temperature lapse rate at different level. So here we compared the temperature lapse rate at 4 different levels. So here surface to 3 kilometer, and then 3 kilometer to 6 kilometer, and as well as in the right panel you can see 500 millibar to 850, and then also 500 to 700. So this is at different levels. So at the bottom level, at the mid level, and the upper level. So this is the this adiabatic temperature lapse rate also define the characteristics of the 3 different types of supercell. And then like the precipitable water, as if in the left panel, it says that the precipitable water so it is the lowest 400 millibar, and you can see that for that with the lowest amount of precipitable water, it produces a low precipitating supercell, although that HP and the classic supercell share at least the same amount of water, but later on I will be explaining why it we define that one produces the HP and another produces the classic. In the right panel, you can see that mean mixing ratios. So where again you can see that the bottom, like in the boundary layer, like the bottom 100 meter of the troposphere. So where you can see that one of the lowest, when there is the lowest amount of rain, like water vapor in the atmosphere, and we receive the LP supercell, and that is exactly what happened last year. So when there is a catastrophic wildfire in all three directions, in the like in the west, in the north, and also in the southeast. So wildfire, those wildfire is coming over the the prairies, and those making an obstacle of the heat is coming to the sun, the surface, and that is why actually when we received that last year, we received a very less amount of rain, and that means in terms of we received the less amount of high precipitated supercell compared to, again, we received more LP supercell. So these studies have also some significance that under future climate change, if we see more wildfire, then actually there is a risk of, okay, we receive that more LP supercell compared to the HP supercell. And that's last seen in comparison, we can see the bulk reception number. This parameter compare buoyancy, that the buoyancy over the vertical wind shear. So this is the trade-off between mechanical forces and then the dynamical forces. So this is the trade-off between these two forces. And you can see here that when there is a very high wind shear and with the lake wave, again, we see the resultant values. Again, the bulk reception number is a very small values compared to in the LP supercell, sorry, classic supercell. There is the trade-off between the buoyancy over the vertical wind shear, and that's why we say that here the value is the medium compared to the HP supercell, where we see the higher cap, a very lowest amount of shear, and that is when we receive the HP supercell. And I wanted to mention that here that this is in the Canadian prairie, so they show a really distinguished characteristics. LP supercell dominate over Alberta, classic supercell dominate over the Saskatchewan, and HP supercell dominate over Manitoba. And so this is another one, and that so until now I was showing the comparison between LP, HP, and classic supercell over the Canadian prairies. Now you can see in this plot the comparison between the one of the LP supercell with its US counterpart. So I am trying to see that how Canadian prairie supercell, whether the Canadian prairie supercell have a distinctive characteristic compared to its US jet plane counterpart, and the answer is yes. As you can see, the blue color indicating the Canadian LP supercell, and the red color is showing the variable corresponding to the US jet plane low precipitation supercell. So this is I'm comparing three different wind variables here: bulk wind shear, as I mentioned, the 1 kilometer, 3 kilometer, and then effective inflow rate. So again, you can see the very clear difference between Canadian and the US jet plane supercell. And the right panel, you said a strong relative helicity. Again, you can see a very significant difference between US and the Canadian prairies low precipitation supercell. And this is the dynamical variable. Again, we see the very characteristic difference between the US and the Canadian prairie supercell. And so this is I'm showing only for LP supercell, and we receive the similar kind of pattern for the HP supercell and the classic supercell when you compare the Canadian Canadian prairies HP and classic supercell with the US Great Plain. So the conclusion from this year, we see clearly that the dynamical and thermodynamical characteristics of the Canadian prairies LP, HP, and classic supercell, there is significant difference. And we see, as I said, okay, as I mentioned, that we see similar precipitable water, but a difference on the mixing ratios. So that makes the difference between classic supercell and the HP supercell. Another is this, okay, we see that in the HP supercell, we have a very comparatively lower downdraft cap than the classic. So downdraft cap, when it is strongly, create a strong wind, and which may cut off the inflow. That means the inflow, the warm moisture is coming to the core of the updraft of the thunderstorm. It is when there is a high value of decay, it is cutting off the supply, and that's why actually that one of the LP super, like the classic supercell, is producing comparatively a lower amount of rain than the HP supercell. And we see that LP supercell show the lowest amount of precipitable water, min-maxing ratio, storm relative helicity, cap, and burn bulk reception number shear. And all together, these values is producing an environment, and that is triggering low precipitation of supercell. And overall, the dynamical and the canonical characteristics between Canadian Prairie's supercell is significantly different than their US Great Plains counterpart. And this is the little reference, and thank you very much for your attention.
Okay, thank you, Mustafa, for your presentation. Any questions for Mustafa from the audience? Okay.
There's a question.
I have a quick question for Mustafa, if that's okay.
Yeah, go ahead.
I was wondering, Mustafa, how did you identify the supercells? Because I'm not sure you mentioned that.
Okay, yeah. So I think the supercell is really unique because each supercell produces a rotating updraft. So that means a mesocyclone. So the rotational structure of the cloud. So we see here from like for me, I followed a little unconventional methodology. At first, I received like thunderstorms picture from professional storm chaser. So that is like you can say like a transdisciplinary research in my case. Like I make collaboration with them, so get the data from them, and then I distinguish that LP supercell, HP supercell, and then those classic supercell based on the picture. And then actually I cross-check with the radar echo, reflectivity echo, where I see that a clear hook echo shape on the radar reflectivity.
Okay, thanks.
Mm-hmm.
Yeah, Mustafa, just wondering, like the analysis you showed, like CAVE or whatever, are you using wolf output or reanalysis data?
No, these are fully raw data, radio sounding data. These are all observational data.
Okay, I think you'd better mention it at the very beginning. Otherwise, it's a little bit confused. I think, and the radio sound data is limited for locations. How can you capture these supercell thunderstorms when, like, if the sun is a little bit away from that? Can you still say it's representing the case?
Yeah, as you can see that like I show in the map at the beginning, like here in this map, that here like specifically the largest number of sample in my study is comes from the South Saskatchewan. And the radio sounding data I'm using that Glasgow radio sounding observation, and which is I think that the proxy sounding. I say this is the proxy sounding, which is like all the sample I analyze is less than 400 kilometers in the upwind direction. So this is one of the methodology. And other cases for Alberta, I use Edmonton Eastern Plain sounding, and then for the Manitoba, I use some La Paz sounding. And I think some of the sounding, I think University of Manitoba, they release some like occasional sounding during a severe thunderstorm days. I think I retrieved some of the sounding from there. And in the complete absence, I use that global forecast system like analysis data.
Okay, yeah, thank you. Okay, okay, let's move on to Muhammad. Hello, have you fixed your microphone?
Hi, can you hear me now?
Yeah, good.
Yeah, great. Thank you so much. I'm sorry for this technical issue. I'm going to share my screen.
Okay, yeah.
So I'm going to talk about an extreme value-based likelihood ratio test to evaluate BCC-AQ version 2 capability for downscaling projecting future unprecedented precipitation extremes. So my outlines, I will talk about the context, the first general concern, then the specific concern, then I'm going to conclude. So in Canada, the principal source of downscaling future precipitation is statistical downscaling using the BCC-AQ version 2 approach. So statistical downscaling procedure, we take the climate model simulation over a suitable period, and we calibrate the BCC-AQ using high resolution gridded data. Then over future period using climate model simulation, we apply the calibrated transfer functions to obtain future higher resolution gridded data sets. Okay, concern in this approach is that the BCC-AQ transfer function will not change until the future climate conditions. This assumption, however, cannot be tested using observations because we lack future observations. A way to test this assumption, the stability of the BCC-AQ transfer function, is to work on a perfect model work. In that case, we're going to use data from daily precipitation over southern BC and use CAN-RCM large ensemble model, and then to be downscaled to WRF resolutions, WRF simulation over Western Canada. We're going to use WRF simulations that have been developed by Yan Ping and her team. We use for WRF simulations, historical control simulation from 2001 to 2014, and future pseudo-global warming simulations corresponding to the expected climate from 2086 to 2099 under the RCP 8.5. So in the perfect model approach, we're going to test the stability of the BCC-AQ transfer function. We take from a historical period one member from CAN-RCM4, and we calibrate the BCC-AQ transfer function. And then we apply this calibrated transfer function to that member to obtain downscaled results of the historical period, and then compare with the CTL work, the control period of work. We're going to take the same member and take the futures, the pseudo-global warming, the corresponding to the global warming simulations from that member, apply the same transfer function calibrated here to obtain future downscaled results, and then compare with a pseudo-global warming work. Now we're going to take another member from CAN-RCM4 and use the same calibrated function. The member 2 here is not used in the calibration. It is out of sample member. And we apply the calibrated BCC-AQ transfer function using the model, the member 1, to downscale this data over the historical future condition. And then we compare with both. We take the same member that is not used to calibrate BCC-AQ over the future and apply the BCC-AQ transfer function to obtain future results, and then compare again with both. So the member that we used here to calibrate BCC-AQ transfer function is going to be called in sample member 1. And the other member that is not used to calibrate the BCC-AQ transfer function is going to be called out of sample member. So in our comparison, we're going to focus on precipitation extremes, mainly on annual maximum. So we're going to repeat this process using other in sample member and other out sample member. We're going to repeat that till we get 50 members in order to build knowledge about the impact of internal variability in downscaling evaluation and performance. So I show here some results for the percent bias of mean of annual maxima from the 50 downscaled precipitation series using the 50 out of sample members and the 50 in sample member of CAN-RCM4 simulation for the control period and the pseudo-global warming period. You can see that bias are substantially higher over the pseudo-global warming period compared to the control period. So the relative root mean square errors is also higher over the pseudo-global warming period compared to the control period. Now we move our attention to a specific concern, and we need to investigate the potential of the BCCAQ to generate unprecedented extremes under present and future climate circumstances. To this end, we take annual maxima from the WRF, and we take also annual maxima from the BCC, downscaled annual maxima using BCCAQ. So to be able to reproduce unprecedented events first, the BCCAQ should reproduce the mean of annual maxima. But however, this is not enough. It must also reproduce the variance of annual maxima. But also this is not enough. It must be able to reproduce the rate at which the variance increase as the length of block maxima increase. And this rates characterize how large the value gets large. So if you want to obtain this parameter, a way to obtain these three parameters is to fit the GWF distribution. So the GWF distribution, it helps us to reduce the body of extremes into a skeleton, telling us how large this value gets larger. So if BCCAQ is able to reproduce unprecedented event, he must reproduce a skeleton that is significantly not different than the skeleton provided by the WRF specification. So here in our hypothesis, because the hypothesis H0 that θ1 equal to θ2 against the alternative hypothesis, θ1 is different than θ2. And to do that, we're going to use extreme value-based likelihood ratio statistics. This statistics is compare the log likelihood of the GWF models using the basic model under the assumption that X1 and X2 may exhibit different skeleton of extremes. However, we compare this with the hypothesized likelihood by fitting the MLE to the combined dataset under H0 is true. So this statistics is going to follow a P-square distribution with degree of freedom K minus Q, where K is the number of functionally independent parameter in the basic model, and Q is the number of independent parameter in the hypothesized model. In our case, K is equal to 6 parameters. These are 3 parameters for the WRF annual maxima GWF and 3 parameters for the BCCAQ GWF distribution. And under the hypothesized model, the number of parameters are 3 because we assume that the 2 parameters in GWF, in WRF and downscaled BCCAQ are similar. So we show here, so this way we show here some result of the p-value for pseudo-global warming and the control periods for each 50 ESM and 50 OSM downscaled precipitation annual maximum. You can see that the p-value is substantially large over the control period. It's a bit lower over the control period when we use members that are not used in the calibration of the BCCAQ. Over the pseudo-global warming, the p-value is substantially reduced. So at a 5% significance level, we reject the hypothesis that the 2 parameters of the fitted GWF are equal. We reject this the H0 at 5% over the control period. Using outsample numbers, we reject it at 16% over the study area. However, for the pseudo-global warming period, the rejection is substantially very, very higher compared to the control period, with approximately 51% in both ESM and the OSM numbers. So in conclusion, BCCAQ downscaling results agree with the targeted WRF simulation over the calibration periods. However, performance was substantially lower when operating in warmer future conditions. And in conclusion, we should think a little more deeply about the impact of using transfer function that is strongly affected by warming signals and how to reduce its related bias. So thank you so much.
Okay, thank you, Mohammed, for the presentation. Any questions from the audience? Oh, Francis.
Okay, thanks very much, Benali. That's nicely done. Do you have any thoughts on how long the calibration data set should be in order to reduce these discrepancies in the projected future climate and downscaled future climate?
Yeah, I don't know. I didn't investigate that question. So this data are used using 40 years or 14 years of data. However, we used like a bootstrap approach to increase the amount of data to take additional information from nearby location in order to increase the sample of the dwarf sample to approximately 70 years. It's going to inflate a little bit the volume of data, but I didn't yet investigate the impact of the sample size on this result.
Thanks, Benali.
Thank you.
Alex.
Hi, Benali. That was interesting. I'm wondering about this though. The WRF simulations are in the future. It's a pseudo global warming experience where it's perturbed air interim boundary conditions. Is that correct? Whereas the CAN-RCM4 large ensemble is a free running transient simulation that's forced with CAN-ESM2. So isn't there going to be a fundamental difference in the climate that those two simulations reach at the end of the 21st century? And wouldn't that account for some of these differences?
Yeah, this is, thanks, Alex. This is an interesting question. We actually try to answer that there are maybe a bias that is due not to the fact that the BCC AQ transfer function is not due to the stability of the BCC transfer function, because the warming that is prescribed to the CAN-RCM may be different to the warming that is prescribed to the WRF simulations. And a way to do this is to try to account for the bias, for the difference in this warming, and to include this, to reduce, to eliminate this bias, and then to do the assessment again. So we have to think, but there are many possibilities of bias other than the stability of the BCC AQ transfer function. And one of them is the warming that is prescribed to CAN-RCM4, and the warming that is prescribed in the WRF simulations, and how to eliminate the effect of this bias. Thank you.
Okay, thanks, Mohammed. Let's move on to our next speaker. Our next speaker is Emily Cadena.
If I could share my screen now.
Sure. Oh, yeah.
So I hope you can hear me well and see my presentation okay. So thanks, Yanping, and hi, everyone. My name is Émile Cardinal. I'm a master's student at the Université du Québec à Montréal, UQAM. And today I will present you part of my thesis project, which is the climatology of and factors contributing to the occurrences of near zero conditions at Terrace, British Columbia. So let's jump ahead with the scientific overview. So first, where are we? So the city of Terrace is located in the center-west portion of the province. It is an important regional hub, and the Trans-Canada Highway passes through the city. It's fairly north, so we're at 54 degrees north, only 120 kilometers away from Alaska, and about 100 kilometers from the Pacific Ocean shoreline. So in terms of geography and climate, it lies at the heart of the coastal mountain range, at the intersection of two deep valleys within the mountains, and we have a broader valley aligned north-south. So we have 1,350 millimeters of precipitation on average each year, 25% of it falling as snow, and we have much more precipitation in the winter time. So what gives the localized climate that we observe at terrace? It's a combination of multiple things. So basically orographic precipitation, atmospheric rivers coming in from the ocean, but also since we're fairly north, we have the influence of the Arctic ice genesis that occurs in Northwest Canada. And this Arctic cold air can drain in the valleys of British Columbia in form of Arctic outflows. And this could be even more present with the wind channeling in the valleys themselves. So basically, we are in the situation where we have ample precipitation and moisture combined with a battle zone between cold and warm air. So because of that, we're hovering close to the 0-degree isotherm a lot during the winter time with lots of mixture of precipitation that we see in terrace. So talking about the 0-degree isotherm or near zero conditions, which are defined as any temperature between -2 degrees Celsius and 2 degrees Celsius. Eva Mekis and her team did a study, climatology of these conditions throughout Canada using a station-based climatology. So we have a north-south and east-west variability due to radiative budget and continentality. But they used the terrace station, which is highlighted here with the red arrow in their study. And the numbers that we see at terrace are very big numbers for these conditions. So we have the frequency or the count or the number of hours of near zero conditions throughout the year, which is panel B here. And terrace has about 1,800 hours of near zero conditions throughout the year, which is about half of all the wintertime hours, which is very, very impressive. It's a very big number and it's an outlier for all Canada. And we also have the intensity or the duration of an event. An event is defined as consecutive hours of near zero conditions. And terrace in the study of Mekis et al. Had durations exceeding 90 hours for the maximum duration, but it can reach 200 hours straight of near zero conditions. So the goal of my study is really to understand what gives these specific conditions in terms of temperature in terrace. And it's very important to study those because any precipitation type can reach the surface between -2 and 2. And long events can lead to high impacts on society if there is freezing or mixed precipitation in these long events. So how to do so? Well, first we'll start by developing a local climatology based on stations from ECCC and local BC government stations that are surrounding terrace. So here is the network that I chose. So we have different heights, climates, and variable distances from the Pacific Ocean. So we have hourly wind and temperature for all the stations. And for the ECCC stations, which are highlighted here in the boxes, we have also precipitation types with MANOPS at each hour. So these color code will come back to my presentation. We can go back in time to 1956 for the ECCC stations and between 14 and 32 years before 2020 for all the other stations. Also, to put more emphasis on the precipitation and the local conditions that we observe at terrace, we installed a weather station for that. So we use multiple instruments that we installed on the rooftop of the UNBC University campus at terrace. So we have a vertical radar for precipitation velocity and the Doppler velocity and the reflectivity on the vertical profile. We have an optic dastrometer for particle size and speed. We have an ice detector for ice accretion at the surface. We have a hobo tipping bucket rain gauge for liquid precipitation accumulation. And then we have basic temperature, wind, and humidity sensors. We combine all these data with the ERA5 reanalysis data to have a larger view of the synoptics of the atmosphere so we can do case studies. So that's how we're going to proceed. So let's jump with the results. So here I'm showing a frequency intensity graph. So the x-axis is the number of events on average on the climatology, and the y-axis is the mean duration of those events. And on the top left, you have the map with the color code of the stations for reference. So we see the negative trend. So the more events we have of near zero conditions, the less long they are. This is only logical for time continuity reasons. But terrace stands out as having less events, but longer ones. So we have a mean duration of about 11 hours of near zero conditions when we have those at terrace. So I would stay in the same idea. So on this graph, the y-axis is the same. So it's the duration, the mean duration of the event. And then I go in a bit more details. So the x-axis are the pathways, and these are shown in the bottom left of the screen. Basically, it's whether we're warming up or cooling down in the events themselves. And I decided to choose them again for the 3 ECCC stations, and I splitted them even more with precipitation. Those that didn't contain any are the white circles, those that contain at least 1 hour of any precipitation in the events are the gray squares, and those that contain freezing rain and ice pellets as well. So first, we can see that when there is no precipitation in the events, the duration goes down. And terrace has the highest average duration of the events of between all the stations, so Prince Rupert and Smithers. And as soon as we have 1 hour of precipitation, the duration goes up for all the stations. So the mean duration goes up to 18 hours for the event duration at terrace, and to 39 hours of a mean duration when we have freezing precipitation. So either freezing rain or ice pellets, which is really, really impressive. So we can see the importance of precipitation and water on all its phases, controlling the duration of near zero conditions. So to go a bit in more details on the weather that we observe in terrace, here I'm showing the wind roses. So panel A is the surface wind on the climatological timescale, and on panel B, when we have precipitation. So basically we see the north-south bimodality of the winds aligned with the broader valley that is located at terrace. So when I put in the freezing rain and ice pellet wind roses, so when the hours when these fell, so C and D, we see that the southerly wind just disappear, and we're only left with northerly winds pretty much. So this is an evidence of cold, stable layers trapped at the surface with temperature inversions. And this is also an evidence of pressure-driven channeling. So finally, I will explain to you a case study. So I chose a case study in which we had a long near zero condition event. So basically, this is a meteorogram, or the evolution of meteorological conditions at the station that I explained earlier. So panel A is the temperature, B and C is wind speed and wind direction, and D are the precip types that were observed at the terrace airport. So we had a long transition between snow and rain that took place in stages, and we have warm air advection pretty much throughout this event. And first, we have freezing rain and ice pellets at around -10 degrees at the surface, which is an evidence of a very, very strong temperature inversion taking place here. But also look at what happens when we reach 0 degree. We just lock there for pretty much 24-hour long period while precipitation was falling. So basically at the 0 degree mark, it's a diabatic processes, or the precipitation, are very important because it's an equilibrium between latent heat release, cooling by melting, and evaporation of precipitation that makes the conditions just stay at 0 for long periods of time. So we have evidences of that in multiple case studies that I looked. So here it's the same thing for the same case study. Panel A are the precipitation accumulations, and D and E are on the vertical profile, the reflectivity, the radar reflectivity, and the Doppler velocity shown with the MR, or the vertical radar. So we had 4 millimeters of ice accretion that fell, or freezing rain that fell in terrace during this event. And we can see on top, so about 600 meters above the station, we had a melting layer. So we have a bright band evidence. So the precipitation was melting in above 0 degrees Celsius conditions. So this moist above 0 layer this melting layer was supported by an atmospheric river. So here I'm showing the IVT maps over the Pacific, and this moist warm air just flowed above the mountain line. So at 800 hectopascals, above about 2 kilometers above the surface, we have very warm air advection that took place with southerly winds above terrace. So we see really 2 different scenarios, one that is occurring above the mountain line and one at the surface. And basically what stands out is how easy it's possible to form freezing precipitation in the area. So we have the atmospheric rivers coming in, flowing above the mountain lines. And at the surface, we have pressure-driven channeling, cold air stable layers that are trapped at the surface. And we can have with that temperature inversions that form really, really easily. And this kind of setup that generate freezing precipitation in terrace. And these freezing precipitation then lead to long near zero conditions. So that's a summary here. So we have very long and a high frequency of near zero conditions that is observed at terrace. Basically, the factors that control these are very high precipitation levels, freezing precipitation, and cold air that is trapped in the valleys and that can resist to warm air advection due to the channelings in the valleys that take place. And basically, it's a combination of atmospheric rivers, freezing precipitation, and wind channeling that makes freezing precipitation and long near zero conditions possible in the area. Thank you. Can answer some questions if you have any.
Yeah, thanks, Emily, for the nice presentation. Any questions from the group? Okay, yeah. Well, I just wondering, like, I think it's a nice piece of work study, like based on observation. Do you have any plan to make it useful for the model development or something like for the future work?
Yes, that comes up all the time. Yeah, I didn't use any model because of course, if I would have used a model, I would have a better 3D representation of what's going on at the micro scale around terrace. This is left for future work, and I know there will be some future work with that, like really choosing what I discovered based on all the information that I presented to you. And I know models and simulations could be done in the future to see whether climate change will have an impact on that, because we want to project that as well in the future. But it's really a battle between more precipitation, so more stronger atmospheric rivers coming in the area, but also these precipitation could lead to more 0 degree conditions. So it's really a battle, and this is left for future study. So yeah, it's very interesting.
Yeah. Thanks, Emily. That's yeah, that's a good plan. Okay.
Thank you.
Yeah. So we are done with the oral presentation part. Next will be the post presentation, and for each post presenter will give 2 minutes for lightning talks. So just wonder, Carol Roman, are you there? Can you give 2 minutes lightning talks?
Okay. Well, hello everyone. My name is Kyle Human, and I will briefly present my current research, the investigation of the wet snow events leading to power outages over New Brunswick using convection permitting simulations. Okay, well, first, one question, well, why study wet snow events? Well, beside the fact that snow is one of the coolest form of precipitation, when it's too much of it, it can lead to damage. So, well, the wet snow, it's thicker and heavier than snow, and when associated with moderately strong wind speeds, it leads to increased accretion, making the fall of trees and power lines more likely. I think you can see in the picture, or he's on the left, where huge amounts of snows are agglomerated on the tree branch. So the wet snow, it needs sticks and getting heavy and can make it fall. Okay, so identifying and understanding these events can help power companies prepare for it and reduce the numbers of hours customers are left without power. So here in this figure, you can see a snowstorm event that happened in New Brunswick. The plot is from Bathurst, from January 1st, 2010, and which was the New Year weather bomb. So the wet snow happens in near zero temperatures. So I can see over here from the start of the snow and to the end, and the combination of the high winds and the 40 centimeters of snow made this event very messy. So we should come see my poster tomorrow. Where you can see more details of these events and more cool information about extreme events over New Brunswick. Okay. Thank you. That's very short, 2 minutes.
Okay, thanks, Carol, for the presentation.
Okay.
And we have another poster presenter.
That's me, Andre.
Yeah. Andre Bortonsini. Can you give a...
Yeah. I'll share my screen here.
Sure.
Okay, yeah, first, my name is Andre Bertoncini, as Yang Penny said. I'm a PhD candidate working with John Pomeroy. And in this work, we also had the help of Julie Tureau from UCAM. And yeah, so basically, I just want to invite you all to come check my poster tomorrow. This poster is entitled Establishing Reflectivity Snowfall Relationships for Different Particle Size Distributions in the Fortress Mountain Research Basin. So basically, the aim of this study is to develop hydrometeor-specific reflectivity snowfall relationships in order to improve satellite snowfall estimates in the complex terrain of the Fortress Mountain Research Basin in the Canadian Rockies, Alberta. And here we are looking specifically to improve the estimates of the GPM satellite. And so basically, in this study here, we had particle size distribution data from a parcel 2 hydrometer. We also had reflectivity data from MRR that it's installed at Fortress Mountain. And also we had snowfall gauge data from the Fortress Mountain. And we look at 2 different methods to retrieve these relationships. One is empirical, and the other one is theoretical. And then we find out that the theoretical method, which is this one here, although the bias is high, it was the correlation was higher and the spread was not too high in this case here. And we saw that this method could be the most useful to improve the satellite estimates, but with the caveat that it needs to be corrected for bias using surface observations from a network of gauges. So yeah, please come check out my poster tomorrow at the poster session. Thank you.
Okay, thanks, Andre, for the nice presentation. So this is the end of this scientific section, and we will have a 30 minutes break. And after that, there will be a panel discussion on extreme events, and I hope you guys will come back after 30 minutes. Thank you.